Welcome! The objective of this video is for any solution be able to calculate the pH, pOH, concentration of hydrogen ions, and concentration of hydroxide ions. In our previous video, we talked about acids and bases. Well, we can go into a little bit more detail about these acids and bases. Some acids and bases are considered strong, while some are considered weak. This is based on how much of our original acid or base reacts, turning into the conjugates, turning into the products. As it turns out, some of our acids and bases react completely, and we end up with only the conjugate of those acids, or the conjugate of those bases. This is actually a little bit uncommon. Most of our acids and bases only react partially. Sometimes we have 90% of our original acids just doing nothing, and maybe 10% or 5% or 1% of these acid molecules actually turn into H+ and the conjugate base. This is described as the strength of our acid, or the strength of our base. And be careful here, this is independent of our concentration. We can talk about the concentration as how many molecules you start with, and the strength of our acid or base as what percentage of them are able to react. Strong acids or bases completely react. Every single molecule will turn into that conjugate. And we can denote that using a single-sided arrow. Weak acids and bases are more common. Actually, they only partially react. Only a handful of molecules out of every 100 or 1,000 are able to turn into those products. We're going to denote this with a double-sided arrow. Here is what that can look like. HCl is one of our strong acids, and it will turn entirely into our products. What we will see are only our products of Cl-, H3O+. If you look in your beaker and try to find any HCl, you'll see that it is not there. It is gone. We only have the conjugate base, which in this case has to be Cl-. As it turns out, this is an uncommon situation. When water is your solvent, we only have 6 strong acids or maybe 7 strong acids that you will come across. HCl, HBr, HI, acids from these halogens that are not fluorine, and then nitric acid, perchloric acid, and sulfuric acid. Every other acid that we see, we can assume that it is going to be weak. We have some good news here. The math for these acids is very simple. The concentration of H+, if you want to enumerate how much H+ is around, it will only depend on our initial concentration of the acid, because every single acid molecule will break apart and form those H+ ions. On the other side of the coin, we can talk about weak acids as ones that only partially ionize, only partially react. For our course, we're not going to worry about doing calculations here in terms of how much of our products are present, how much of our initial reactants are present if you're doing this reaction. It's possible, but we'll save that for a future course. Instead, we can note that when we do have these weak acids, almost all of them are going to stick around as that original molecule. In our beaker, we can see that we have mostly our HF. Here's 1, 2, 3 of those HFs. And we have only a few of our products, H3O+ and F-, in our beaker here, we have 1 out of every 4 is able to turn into those products, much, much less than 100%. In real life, this might be 1 out of 4, it might be 1 out of 10, it might be 1 out of 1,000. It depends on the molecules that we have. We can look at a picture real quick. Based on these images, which of these is a weak acid? Well, weak acids are going to have mostly our original molecule hanging around. Here, our image all the way on the right, beaker C, has mostly this HCHO2 acid molecule, and only a handful of them have broken apart into those products. This is what it means to be a weak acid, to have mostly your original starting material, and only a fraction of them are able to react and turn into our products. The same sort of logic applies to our bases. Strong bases are ones that completely dissociate into their component ions. Here we have sodium hydroxide. When it dissolves, we have sodium ions and hydroxide ions. Every single one of those sodium hydroxide units has been broken apart into those pieces. We have only our products. And we have exactly none of our original formula unit present. Our strong bases are easy to remember. They're simply the hydroxide compounds that form when you have a group 1 or group 2 cation. Again, the other situation is a weak base. These weak bases only partially react. They only partially ionize. Again, we'll save the calculations for a future class, but we can see that we have mostly our starting material and only a few of our products. In this image on the right, we have 4 of our ammonia molecules that have not reacted, and only 1 of them that has reacted. Again, in real life, this might not be 1 out of every 5. It might be more like 1 out of every 100 or 1,000. Here are some example problems. If you have HCl, this is a strong acid. If you have 1.5 molar of your HCl, we can try to find the concentration. Here, our square brackets means concentration of whatever inside those square brackets. Since HCl is strong, we are going to have all of it turn into our H+ and Cl-. So we were going to have exactly the same concentration of our H+. And here H+ or H3O+ could be the same thing. For our second example, NaOH is again a strong base. Every single one of these NaOHs will break apart into Na+ and OH-. Because of that, we'll have exactly the same amount of OH- as we had for our original NaOH. Calcium hydroxide is strong as well, so this is going to 100% of the time break apart into our calciums and our hydroxides. Let's keep account of the stoichiometry. Every calcium hydroxide is going to turn into 2 hydroxides. So actually our amount of hydroxide is going to be exactly double the amount of our original calcium hydroxide. Lastly, we have a weak acid, which means we're not quite equipped to do any calculations yet, but we can estimate here if we have 1.5 molar as our concentration, this weak acid is not going to break apart completely, so our amount of H plus is going to be less than what we started with. Once again, we'll learn how to do these calculations eventually, but we'll save that for another time. All right, so we can predict the amount of H plus or OH minus in a strong acid or strong base solution. Now we want to introduce a few new equations to calculate and convert between these concentrations. As it turns out, the amount of H plus and OH minus in our solutions are related to each other. In fact, they are inversely proportional. We have an equation here that says our H plus multiplied by our OH minus is going to be equal to this number, 1 times 10 to the negative 14th power. We mentioned this before, but anything inside of those square brackets can be referred to as concentration of whatever in units of molarity. This equation is really nice if we can measure the concentration of one of these things, either H plus or OH minus. We can use this equation to solve for the other one. We can also see a nice relationship here. H plus compared to OH minus is almost like a little seesaw. If you have exactly equal amounts of H plus and OH minus, this is going to be considered neutral. In acid solutions, this seesaw is going to be tipped towards the H plus. We're going to have more H plus and less of our OH minus. For bases, the opposite will be true. When you have extra hydroxide compared to your H plus, your solution is going to be basic. If you want to actually do some calculations, you can get some numbers here as well. In order for your solution to be neutral and for H plus and OH minus to be equal, their concentrations have to be exactly 10 to the negative 7 molar each. In order for your solution to be an acid, our concentration has to be more than 10 to the negative 7 in terms of H plus. The same is true for our bases. In order for something to be basic, our concentration of hydroxide has to be more than 10 to the negative 7. Just like a seesaw though, if you're increasing the amount of OH minus, you have to be decreasing the other side. Or if you're increasing the amount of H plus, you have to be decreasing the amount of OH minus. This is one nice way of deciding if you have an acid or base solution. Calculate the amount of H plus, calculate the amount of OH minus, and compare which one is bigger. Or simply calculate one and compare that to your neutral value of 10 to the negative 7. Extra H plus means that the solution is acidic. Extra OH minus means that the solution is basic. We were talking about these numbers, 10 to the negative 7th molar for H3O plus or OH minus, but these concentrations of H plus or OH minus are really small and not very convenient. Instead, we can quantify how acidic or basic something is using the pH scale. The pH scale is a logarithmic scale, which means each value, each unit in the pH scale is worth a 10 times change in concentration. Essentially, we are condensing 14 orders of magnitude in terms of concentration into simply 14 digits in pH. Our concentrations can go from all the way down here at 10 to the negative 0, all the way up here to 10 to the negative 14. A wide range of concentrations. But our pH scale goes from about 1 to about 14. These numbers are more convenient and more pleasing for us to use. The neutral situation is when you have equal amounts of H plus and OH minus. This corresponds to exactly a pH of 7. When you increase the amount of H plus that you have, you are going to decrease the amount of OH minus that you have. That was that seesaw idea we had in our last slide. And as you get more acidic, the pH is going to get lower. Alternatively, if you add extra hydroxide to your solution, the concentration of H plus is going to have to get smaller. Again, because of that seesaw inversely proportional idea. And the pH is going to become a higher number. We can calculate the pH numerically using this formula. The pH is the negative log of our H plus or H3O plus. If we want to do the opposite, we can calculate our concentration if we know our pH. The concentration of H plus is 10 to the negative pH. This is great. Now we have a toolbox of 3 nice equations converting between concentrations and pH. We have one more scale that we can introduce. This is the pOH scale. It is completely analogous to the pH scale, except it's the opposite. It's based on our amount of hydroxide instead. For pOH, the pOH of acids is going to be bigger than 7. And for our bases, the pOH is less than 7. It's exactly the upside down version of pH. This is our definition for the pOH. Take the negative log of your concentration of hydroxide. If you're trying to do the opposite, you can calculate the amount of hydroxide based on the value of the pOH. One last relationship here, our pOH and pH are related to each other. As it turns out, they need to add up to a total of 14. We can do some example problems. Here we know the concentration of H3O+, and we want to calculate everything else. We have 6 equations that we can use in our toolbox, and only 4 values that we're converting between. That means there are going to be multiple ways of attacking these problems. You can go and use any of those equations in whatever order. So my method here is not the only way of solving this. That being said, I'm going to start here trying to solve for the pH using our formula for pH. What we find is the pH has to be 2.403. Next, we can attack this pOH problem based on this relationship between pH and pOH. Our pH is 2.403. Our pOH has to add up with that to get a total of 14. Lastly, we can find our amount of hydroxide. Again, multiple ways to try to do this. All of them should end up with a nice final answer. No matter which method we choose, we should end up with our amount of hydroxide as 2.53 times 10 to the negative 12 molar. The second problem, we know the pH of our solution. We can try to find all these other variables again. I'm going to start by solving for the pOH using our relationship between pH and pOH. Next, I can use that definition of our pH to figure out our amount of H+. And lastly, we can do something similar to find the amount of OH-. A couple of notes here as we're doing these calculations. This first solution we can see has to be an acid. The amount of H+ is much bigger than the amount of OH-. Or the pH is less than 7. Or the pOH is bigger than 7. All of these point to our solution being acidic. For this bottom solution, we can see that our solution has to be acidic again. Once again, we have more H+ than OH-. And once again, we have a pH that is less than 7. Another thing to highlight, our pH and pOH do not have any units, but our concentrations are calculated in units of molarity. We have a set of practice problems for you all, so pause the video, grab your paper, try to calculate some nice answers. Here we go, we've made it to the end. This is our equation bank. We'll have access to these 6 equations when we're doing our labs and homeworks and exams. No need to memorize here. But we can use these 6 equations to convert between different concentrations, different scales for how acidic and basic our solutions are. It looks like we've accomplished our goals. For our solutions, we can now calculate pH, pOH, concentration of hydrogen ions, and concentration of hydroxide. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.